Picture a universe vast beyond imagining, where stars flicker like candles in an endless night. For centuries, we've gazed upward, peeling back the cosmic veil. Telescopes have revealed galaxies, black holes, and the faint glow of the Big Bang itself, 13.8 billion years ago. We've traced our cosmos from its fiery birth to a distant future where stars fade and matter dissolves. Yet, as we stand on this tower of knowledge, a deeper mystery lingers. What if our universe is not alone? From infinite versions of you to realms of pure emptiness, the multiverse whispers possibilities. In 1920, two astronomers faced off in a grand debate at Washington, D.C.'s Smithsonian. Harlow Shapley, a star mapper of the Milky Way, and Heber Curtis, who'd spotted a strange jet in a distant nebula, clashed over one question: how vast is the cosmos? Shapley argued it was small. Just our Milky Way, with its stars and misty spirals, was all there was. Curtis disagreed, insisting the universe stretched far beyond, with those spirals as separate galaxies, each a starry island millions of light years away. The crowd was captivated, but no winner emerged. The universe's size remained a mystery. Across the country, Edwin Hubble was ready to settle it. At California's Mount Wilson Observatory, armed with the new 100-inch Hooker telescope, he turned his gaze to Andromeda's fuzzy glow. Were its stars faint and nearby, or bright and far? Curtis had already found clues: faint exploding stars, novae in Andromeda, hinting at great distance. But Hubble saw something special: Cepheid variable stars, pulsing with the steady rhythm. Years earlier, Henrietta Swan Leavitt discovered that a Cepheid's pulse revealed its true brightness: faster for dim stars, slower for bright ones. By measuring this, Hubble could calculate their distance. He found them, twinkling in Andromeda's haze. Their slow pulses showed they were giant stars, hundreds of thousands of light years away, far beyond the Milky Way. In 1924, Hubble wrote to Shapley. Andromeda was its own galaxy, and countless others likely dotted the cosmos. Shapley replied, "Your letter destroyed my universe." The cosmic veil lifted, revealing a universe far grander than imagined. Through the 20th century, telescopes grew sharper, stretching our view from millions to billions of light years. But is there an end? In 1964, a faint radio hum from every corner of the sky marked a boundary. The cosmic microwave background, light from 13.8 billion years ago, born when the universe cooled and atoms formed. It's the edge of what we can see, our observable universe, what lies beyond. Einstein's equations and Georges Lemaitre's cosmic egg, the Big Bang's fiery start, suggest our universe is just a piece of a larger whole. If it has no curve, it may stretch forever. Infinite from its birth, even at the Big Bang, it was infinitely dense. Now just thinner, with more galaxies and stars beyond our horizon. As time passes, light from farther reaches should touch us, growing our observable universe. But in the 1990s, astronomers found a twist. Dark energy is pushing galaxies apart faster and faster. In 100 billion years, most will vanish from view, leaving only our local stars against a black void. Today, 2 trillion galaxies fill our observable universe, but 99% are already too far to reach, even at light speed. Beyond, there's likely more. Universes like ours, each a bubble of stars and planets, centered in its own observable patch. In an infinite cosmos, Some bubbles might mirror ours exactly, with another Earth, another you, watching this very video. Max Tegmark calls this the Level 1 multiverse, countless universes, separate forever, beyond our light's reach. This is just the start. Stranger realms await. Why does our universe have its unique rules? Gravity, electromagnetism, the strength of atoms. Everything seems perfectly balanced for stars to shine and life to bloom. In the 1960s, physicist Robert Dicke noted that a slight tweak to gravity or electromagnetism would dim the stars, leaving no room for life. Others, like Fred Hoyle, found that tiny changes in nuclear forces would erase carbon, a building block of life. Steven Weinberg warned that too much dark energy would stretch the cosmos too fast for galaxies to form. Every equation revealed a delicate balance, as if the universe was crafted for us. How could it be so perfect? The answer lies beyond our cosmos in a vast Level 2 multiverse. In the universe's first moments, a burst of rapid growth, inflation, smoothed it out, setting the stage for galaxies. Proposed by Alan Guth, this expansion happened in a trillionth of a second. But there was a catch. How could this burst stop neatly across the cosmos? Calculations showed a messy end. Some regions stopped inflating while others kept growing. This seemed to break the theory, but in the 1980s, thinkers like Andre Linde and Paul Steinhardt reshaped inflation's story. They introduced the inflaton field, a cosmic force driving this rapid stretch. Unlike the old idea, inflation didn't stop everywhere at once. Instead, it became eternal inflation, never fully ending. In eternal inflation, new universes bubble up endlessly, like fizz in a shaken soda. Each bubble forms its own cosmos, separate from ours, carried away by ever-expanding space. Our Level 1 multiverse, with its infinite galaxies beyond our horizon, is just one bubble in this vast sea. Each bubble universe has its own rules. Some have weaker gravity, others heavier particles, or even extra dimensions of space and time. Most of these universes are barren, their physics too chaotic for stars, planets, or life. But a rare few, like ours, hit the sweet spot, balanced just right for complexity and life. Our universe's perfect rules aren't special. They're a lucky roll in an infinite game. This Level 2 multiverse explains why our cosmos seems fine-tuned. We live in one of the few bubbles where life can exist. Yet this is just one idea. Other visions of a Level 2 multiverse wait to be explored, each stranger than the last. Could the universe be reborn over and over, like a story without end? In ancient Hindu tales, the cosmos cycles through 4.3 million years of creation, decay, and rebirth, a dance of renewal. Modern thinkers have wondered, could our universe loop like this? In the 1920s, even Einstein toyed with the idea, his equations hinting at a cosmos that repeats forever. A cycling universe felt comforting, born not from nothing, but from an endless chain of existence. Yet a shadow loomed: entropy. Entropy measures disorder, the slow unraveling of the cosmos. Every action, from a star's glow to a bird's flight, turns useful energy into useless chaos. Across billions of years, disorder grows, piling up like cosmic clutter. If the universe cycles, each new cosmos would inherit this mess from the last. After infinite cycles, how could our universe still hold order, with stars, planets, and life? This flaw seemed to bury the cyclic idea, lost to science's forgotten corners. But some ideas refused to fade. Roger Penrose, a Nobel Prize winner, revived the dream with his conformal cyclic cosmology. He imagined a far future where all matter fades, leaving an empty, featureless cosmos. Stretched, vast, and simple, it mirrors the Big Bang's dawn. Past and future blur, each end birthing a new beginning in an eternal loop. Other minds spun different cycles. In the 1980s, Lee Smolin proposed that black holes, born from dying stars, might tear space and time, spawning new universes. Each black hole could birth a cosmos with its own rules, slightly different from its parent. Some have weak gravity or too few atoms fizzling out. Others, with just the right physics, form stars and more black holes, creating more universes. Like evolution, these thriving cosmos multiply. Fill in Smolin's multiverse with life-friendly worlds. But his cosmic natural selection remains a bold guess, doubted by many. Then came Paul Steinhardt and Neil Turok, who once shaped inflation but later forged a new vision, the ikpyrotic universe. Rooted in string theory, they see our cosmos as a sheet floating in higher dimensions, like a sail in a cosmic breeze. When these sheets collide, a fiery burst creates a new universe with low entropy, solving the disorder problem. Like a phoenix rising from ashes, the cosmos is reborn, cycle after cycle. Yet this idea struggles. Many question universes drifting in unseen dimensions. Still, it sparks wonder, pulling us toward stranger multiverse realms. What if one elegant idea could explain everything? Every star, every force, every atom. Edward Witten, a physicist with an unusual path, chased this dream. Starting with history and linguistics, he dabbled in journalism and economics before finding his calling in physics. By 1976, his knack for untangling the math of space and time earned him fame, culminating in a 1990 Fields Medal, a mathematician's highest honor. But Witten aimed higher, a theory of everything uniting all the universe's rules. He wasn't the first. For decades, physicists struggled to blend the four forces: electromagnetism, strong and weak nuclear forces, and gravity. The first three danced to quantum mechanics, but gravity, described by Einstein's relativity, bends space and time in a different language. This clash frustrated scientists who longed for one universal equation. Early pioneers like Theodore Kaluza and Oscar Klein tried adding extra dimensions to Einstein's work, but their ideas faltered. Even Einstein failed to find this cosmic key. In the 1970s, supergravity sparked hope, proposing particles like electrons have shadowy twins, selectrons, squarks, in 11 dimensions. But its predictions didn't match our cosmos, and supergravity faded. Yet bold ideas linger. In 1984, Michael Green and John Schwartz birthed superstring theory, imagining all particles as vibrations on tiny cosmic strings, like notes on a guitar. This theory, too, needed 11 dimensions, most curled up invisibly in tiny shapes called Calabi-Yau manifolds, too small to sense. Superstring theory promised a unified cosmos, but it splintered into 5 versions, each a different path. By 1995, frustration peaked. At a conference, Edward Witten offered a breakthrough: What if these 5 theories were one? This sparked M theory, where strings stretch into sheets called brains, floating in a higher dimensional bulk. The M might mean mystery, magic, or membrane. No one's sure. M theory shattered hopes for a single, perfect equation. In the universe's fiery birth, physics rules crystallized, but M theory suggests countless ways this could happen, each brain with unique forces, particle masses, or dimensions. This vast string theory landscape could hold 10 to the power of 500 universes, or even infinite ones. Like bubbles in eternal inflation, most brain universes are lifeless. Their physics too chaotic for stars or life. But a rare few, like ours, hit the cosmic jackpot with rules just right for galaxies and us. M theory remains a dream, not a finished theory. Its brains and bulk unproven. Yet to some it feels like truth, a glimpse of universes floating in hidden realms. The cosmic fog lifts, revealing stranger multiverses still to come. What if you're immortal? That no matter the odds, you always survive. Beating illness, danger, even death. It sounds wild, but in the level 3 multiverse, it's a promise. Let's start with light's puzzle. For centuries, thinkers debated, is light a wave or particles? In 1701, Thomas Young, a genius who unlocked Egyptian hieroglyphs, set up a simple test. He shone light through 2 narrow slits onto a screen. If light was particles, it should make 2 bright lines. But Young saw bands of light and dark, an interference pattern, proof light travels. As waves, this idea held for a century. Then quantum physics flipped the script. Einstein showed light comes in packets, photons, like particles. How could it be both? Young's experiment revealed waves, but modern tools show single photons hitting the screen, as dots. Light spreads as a wave, but lands as a particle. Quantum math describes this with a wave function, a smear of possibilities for a particle's position and speed. No exact spot or velocity, just probabilities. Erwin Schrödinger's equation predicts how this wave evolves. It fits Young's slits. The wave splits, interferes, creating the pattern, but one mystery lingers. How does the smeared wave become a single dot? Niels Bohr and Werner Heisenberg offered the Copenhagen interpretation. They said the observer collapses the wave function. The wave is probabilities. High chance here, low there. Measurement forces a single outcome. This explains experiments. The wave spreads through slits, but detection collapses it to one spot. But how does collapse happen? The math doesn't say. It's an added rule, a fix without explanation. Physicists call this the measurement problem. Some say detection does it. John von Neumann even suggested consciousness collapses the wave. Without a mind watching, waves stay smeared. This raises wild questions. Did waves only collapse when the first thinking creature appeared? Sean Carroll calls it embarrassing, a flaw in quantum's foundation. Other ideas emerged, the most daring, many worlds. Hugh Everett, a brilliant teen who questioned Einstein at 12, rejected collapse as a kid's idea during a late-night chat. Everett saw the wave function as real, describing the entire universe. No collapse, just the wave flowing forward via Schrödinger's equation. The lab, experimenter, everything is part of this universal wave. No separate observer. When you measure, the wave doesn't collapse. It splits. In many worlds, every possibility plays out. An electron could be here or there. Both happen in separate branches. The universal wave holds all futures, each as real as ours. Measurement doesn't collapse. It splits realities. In one branch, the electron is here. In another, there. You exist in both, measuring different outcomes. Branches multiply with every quantum event, creating infinite worlds. This level 3, multiverse, nests inside others. Each branch its own infinite cosmos. Many dismiss it as wasteful, with endless copies. Gerard at Hooft called it a stupendous number of parallel worlds. Everett's idea was ignored in his time. Bohr rejected it, and Everett left physics, dying young in 1982. But today, thinkers like Sean Carroll revive it, seeing it as quantum's purest form, no collapse needed. Yet questions linger, like consciousness. What happens to you as worlds split? Are there countless selves, each feeling unique? Philosophers ponder this endless sea. Imagine a coin flip. Heads you live, tails you die. In Copenhagen, it's chance. You might die. In many worlds, the universe splits. You live in one, die in the other. The living, you always survives, immortal in your branch. No matter the odds, a path exists where you win. This is level 3's promise. Endless lives in endless worlds. But is this the ultimate? A stranger level awaits. What is reality? At first glance, it's simple. Tables, water, air, all around you. But look closer and it unravels. Everything is atoms, woven into molecules. Dive deeper, and atoms break into electrons, quarks, tiny bits held by nature's forces. Is this the core of reality? Not quite. These particles and forces follow rules, written in math, equations that shape the cosmos. But where do these rules live? This question pulls us to the level 4 multiverse, Max Tegmark's bold vision. Here, reality is pure mathematics, endless structures encoding every possible universe. Every multiverse we've explored bubbles, cycles, brains, nests within this ultimate realm. It's as if our cosmos is a single equation in an infinite library of possibilities. Imagine our universe as a program, running on a cosmic computer coded by beings beyond us. The level 4 multiverse goes further. Reality isn't a machine, but math itself. No circuits, no creators, just equations existing on their own, each a universe with unique rules. Some hold stars, others chaos, all real in their own way. We've journeyed from our cosmic horizon to bubbles of inflation, cyclic rebirths, and brains in a higher dimensional bulk. Now, we stand at the edge, questioning existence itself. The multiverse isn't one idea. It's a tapestry of dreams. Some, like eternal inflation, rest on solid math. Others, like M-theory's brains, spark hope but lack proof. Many worlds weaves quantum paths, yet remains a theory. Level 4's math. Only reality is the boldest leap. A vision where we're numbers in a cosmic code. Not all embrace the multiverse. Some physicists see it as science's frontier. Eternal inflation, or M-theory, feels too right to dismiss. Others call it unscientific, chasing worlds we'll never see. If we can't test it with telescopes or labs, is it science? Both sides stand on shaky ground. Multiverse ideas are young, their math unfinished. How do bubbles form? Is string theory real? Do quantum worlds split? These questions linger, unanswered. Yet hope persists. Future math might crack open other universes, perhaps through wormholes or patterns in the cosmic microwave background, scars of colliding brains or hints of an infinite cosmos. For now, these worlds hide in the fog of the unknown. Our journey ends here, gazing at realities beyond reach. wondering if we're just a flicker in a mathematical dream. As we drift back from the edges of the multiverse, from infinite bubbles to mathematical dreams, we're left gazing at our own starry sky, wondering what truths lie beyond. This cosmic journey has carried us through realms of possibility, each more wondrous than the last. Thank you for joining us under this vast celestial canopy. We'd love to hear from you. What draws you to these cosmic mysteries? Are you seeking answers to the universe's secrets? Or do these stories spark wonder as you unwind? Share your thoughts in the comments below, and let's keep exploring the cosmos together. Until next time, rest easy and let the stars guide your dreams.